Hello, everyone. It is my utmost pleasure to welcome Dr. Gopal Gupta from UT Dallas to give us an invited talk. Uh, he is a professor of computer science at UT Dallas and the co-director of the Center for Applied AI and Machine Learning at UT Dallas. He was also the Eric Johnson Chair of the CS department till like 2 years ago. Yeah. And he has also presided over many scientific organizations, including Association for Logic Programming. Um, uh, I don't want to spend too much time and cut into the talk, but his research areas span like a huge horizon from PL to logic programming to AI. And in recent times, he has been interested in automated reasoning, explainable AI, and AGI, for example. And his lab has published many papers and developed many actionable software systems that have become the basis of many startup companies. And one important thing is uh, his lab has won the Best Paper Award at ICLP 2016. The Test of Time, sorry, not the Best Paper, the Test of Time Award for their co-inductive logic programming work. And the team was also selected to compete in the Amazon Alexa Prize for Social Bot Challenge 2020-21. And from a personal side, he was a part of my PhD advisory committee.
The most important part.
And apart from all the technical things, I know him as like this very calm, very assuring person. And there were times when I was very tensed about things like filling up my form that I needed to submit. I'm like a last minute person. So so I was trying to fill up a form that you have to submit in order to schedule your thesis defense. So I was very late. I had like the deadline was in 2 days. So he assured me, don't worry, we'll get it done. We'll get it done. So he was just leaving at 5 p.m. I went to him, he's like, what do I do now? So he assured me and we got the things done. And happily, I graduated in time. Anyway, please over to him. And today he's going to talk about his work on automating common sense reasoning. Would you take questions in between?
Yeah,
or?
sure. Please ask. Yeah. So hopefully we will not spill over 1 hour, but if I spill over 1 hour, feel free to leave. Whoever has it or anything.
Okay. The mic is with me. Whoever wants to ask a question, I can run ahead and give the mic. Thank you.
Thank you, Mayuk, for the hospitality and for the generous introduction. So my great pleasure to be here. I actually gave a talk on co-inductive logic programming, which actually relates to the work I'm going to talk about here as well. I think maybe 5 years ago, and in fact that talk is on Microsoft server somewhere. It's on the web, and when people Google me, it shows up. And I actually use it for my logic programming class as well. So it's nice. I can miss one lecture and just play the video, so that helps. Okay, so I'm going to talk about automating common sense reasoning. So quick overview. So what do we want to do? We want to formalize the human thought process, which essentially means automate common sense reasoning, right? The reasoning we do is called common sense reasoning. And the goal is advanced general intelligence. Essentially, we want to be able to reach that goal of AGI by formalizing the human thought process. Why? If we can formalize the human thought process, then pretty much everything can be automated, from automated medical treatment to self-driving cars, to software certification, you name it, and we should be able to, because as humans, we're able to do it. Then obviously, if I can formalize that thought process, I can pretty much automate anything. And how do we do it? So we actually use something called answer set programming, which is a logic programming based system. And I presume everyone is familiar with Prolog or some familiarity with Prolog and logic and stuff. So I'll introduce answer set programming. And then, so the main thing that we have done is that we've designed this. Most of the implementations of answer set programming are based on SAT solvers. So you ground the program, and I'm sure you're familiar with SAT solvers as well. You ground the program, you throw it to a SAT solver, it gives you models. But here we actually designed goal-driven or goal-directed, query-driven implementations. And that was a challenging task we'll talk about. A lot of philosophy I'm going to present as well. So humans are sophisticated and effective thinkers. We operate with just 12 watts of power. And we can perform deductive, abductive, and inductive reasoning, right? Deductive is you're given P implies Q and you're given P, you deduce Q. Abductive is sort of the reverse. You're given Q, you're given if P then Q or P implies Q, and you abduce that possibly P holds. And inductive reasoning, of course, is you observe, pairs of P1, Q1, P2, Q2, and you induce that P implies Q. So it's sort of, you have three things, right? You have the fact, you have the implication, and then you have the consequent. So you give two of them and you get the third, you get the three forms of reasoning, right? So you can actually model deductive and abductive reasoning using ASP and CASP. In fact, I should get my pointer so that everybody can see my pointer. And in fact, we will show that default rules, which are part of answer set programming, are good way of representing inductive generalization. So in fact, I will show you in between a machine learning system as well that is explainable, that performs as well as XGBoost or neural networks or multi-layer perceptrons. So the problem that, so the long-term goal of, or essentially long, short, whatever you want to call it, major goal of AI has been to essentially simulate human intelligence, right? Be as intelligent as humans. And so what are the tools that we have? We have used classical logics and logics for logic programming, Prolog, whatever, for modeling this reasoning. Unfortunately, these logics, we have been stuck with only performing what is called well-founded or inductive reasoning. You really need non-inductive reasoning or what's called co-inductive reasoning as well, and I'll talk about that. Or it's essentially assumption-based reasoning, and it might involve circular reasoning as well, which sounds, somewhat crazy that, I'm talking about circular reasoning. So as humans, we employ both inductive reasoning, which is well-founded, as well as circular or assumption-based reasoning. So co-inductive or circular reasoning is nothing but assumption-based reasoning. You make some assumption, then you draw some conclusions, and these conclusions, from these conclusions, then you may draw your assumption as well, but the whole system is consistent. It's not grounded in anything. You don't know anything as a fact, but still consistent. And we do that all the time, and I'll give you examples. We also draw conclusions from failures of proofs. So classical logic, if a proof fails, it can't do anything. But as humans, we try to prove a query or we try to answer a question and our proof fails. We actually draw some conclusion from that as well. Again, give you examples. So negation is failure, whichever you try to prove something, it fails, and you assume that. So you try to prove proof of P fails, you assume that not of P holds. So that's a key concept for emulating the human thought process. So I'll talk a little bit about the CASP, which is a goal-directed implementation of ASP that supports inductive, co-inductive, and abductive reasoning. And that's actually a crucial component. Although much of the modeling technology is already there within ASP. And in fact, the answer set programming community is the one that has developed all these ways of modeling default rules and multiple worlds and constraints and all kinds of things. So if you look at the history of formalizing human thought, there's all these Boolean logics and predicate logics and other types of advanced logics. And these logics have not been able to model the effectiveness of human reasoning. And a lot of it is, so the way we are slotted into only thinking about inductive structures is because of, problems that were faced 100 years ago. You're probably familiar with Russell's paradox. So Frege invents predicate logic, and then he writes a book and sends it to Russell, and Russell immediately spots a problem, and that where he can show that if you allow for arbitrary predicates to be defined, then you can define predicates that do not make any sense. So he built this set where if R is an element of that set, then R must not be an element of that set, and if R is not an element, so if you're not familiar, read it up. But that was one reason why we stick to inductive structures as itself. So Russell said, the problem was circularity in the reasoning. So he said, you cannot have circular reasoning. Everything should be well-founded. You can only have inductive sets, which means you start from the simplest of objects, for example, an empty set, then you build larger and larger sets by you construct one element set, two element set, three element set, so on. But unfortunately, that cannot model common sense reasoning. So the problem is that these systems of logic cannot reason about themselves. And so Tarski suggested that we have meta-logics and meta-meta logic. So a lot of that is philosophical. So in Kripke in 1975, you're probably familiar with Kripke structures, showed that a language can have its own truth predicate and still be consistent. So basically said you don't need these, you can actually have circular statements and make sense out of them. So this led to the idea of coinduction and modeling of circular reasoning, which we do employ. And from there, so basically so our work in coinductive logic programming that we showed is a key part of being able to model the human thought process. So why do you want to automate common sense reasoning? So for example, I also work with software verification people or software certification people, and they say that human reasoning should be done manually for certifying a piece of software. So there are good reasons for actually automating because human reasoning, because humans can handle only 4 variables at a time. And this has actually been proven by researchers in psychology where, so I just put a quote, if the number of variables to be considered exceeds human processing capacity, then the worker will drop his or her mental bundle and become unable to proceed. So we basically simplify. If it's too complicated, we just give up. So the problem is that, when we reason, we can make statements that are easy to comprehend, but you put them together and we have no idea what they mean. So here's my favorite example that I actually constructed. So suppose you have these 4 statements. Paul will go to Mexico if Sally will not go to Mexico. Sally will go to Mexico if no evidence. Rob will go to Mexico. Rob will not go to Mexico. So the question is, who will go to Mexico? And I don't think you can answer that question. So first of all, what does negation mean here? And there are circular statements here. Paul will go if Sally will not go, and Sally will go if Rob will not go, and Rob will go if Paul will not go. Now you could model them in propositional logic and actually compute a model, right? So who will go to Mexico? We don't know. So formalization, automation is important, and we will accomplish it via answer set programming. So again, common sense reasoning, standard logic programming, and logic fails. In fact, most formalisms have failed, and the problem is that classical logics are monotonic. So common sense reasoning requires non-monotonicity, which means if we discover new information, then we may have to retract our earlier conclusions. So logic is monotonic. It means that once you prove a theorem, it stays there forever. I mean, Pythagoras' theorem has been there, right, for discovered 2000, whatever years ago, proved 2000, and it still is with us because the axioms of Euclidean geometry don't change. But in our day-to-day life, our axioms keep changing. And so since axioms change, I may have to withdraw my conclusions that I might have drawn today, may not be, or something that was not true today may be true tomorrow. So in non-monotonic logics, if you discover contradictory information, it should not break down things as it does in classical logic. As you know, in classical logic, the moment you have a contradiction, everything can be proven. Everything and its negation can be proven. So the way we operate is that we work with the knowledge we have. Whatever we know now, we will make inferences with that. And then if we discover new knowledge, we will revise our conclusion, right? That's how we operate. So for example, I want to get to my home from here. Let's say I work here. I don't think about all the problems that I might encounter on my way to home. It could be things like, there's an earthquake, there is torrential rain, maybe Kim Jong-un launched a missile that landed smack in the middle, my path from here to my home, and so on. But we don't think about it. We say, I'll be able to get to my home normally. And the classic example is that if we know that Tweety is a bird, we conclude it can fly. And this conclusion is to be retracted if Tweety is found to be penguin later, right? We also draw conclusions from absence of information. This is a very critical thing. So you can't tell if it's raining outside. I see that no one is holding up an umbrella. It's drizzly sort of, you can't tell, but no one is holding up an umbrella. So you conclude that it must not be raining. For all we know, those people like to get wet. Or you want to tell if it's cold outside, you look out the window and see if no one is wearing a jacket, you conclude. But those people might be from, North Pole or something, and for them it's really, warm. So, and then we also work with constraints, integrity constraints. So we will not pursue reasoning that violates a violates a constraint that we have in our mind. And also we work with invariants. We know that certain invariants must hold. So for example, we know that it's impossible to walk and sit at the same time, right? So the moment I tell you that, person X is walking, that person implicitly, quickly you can draw the conclusion that the person is not sitting, or that the invariant human must breathe to stay alive. So if I tell you somebody's alive, then you can automatically conclude that must be breathing and so on. So we need to be able to model that as well. And then we also use cyclical or assumption-based reasoning. which allows for multiple words, and that's where we get non-inductive semantics. So an example is, if I ask you, can fish talk in real world? Can animals talk in real world like humans? Obviously, the answer is no. But there is a world, cartoon world of children's books, where animals do talk. So fish can talk in the cartoon world, but not in the real world. So there are really two possible worlds, the cartoon world and the real world. And then we kind of switch context and we figure out, am I in the cartoon world or am I in the real world? And I will perform reasoning over there in that world. And these worlds may have some things consistent. So for example, Nemo the fish can swim in both worlds, the real world. Nemo might be the name of your pet fish, or Nemo might be the fish of the movie, cartoon movie. It swims in both worlds, but it talks in one world and not in the other, right? So there are things that are common, consistent, things that are inconsistent. So we need to be able to simulate this non-inductive reasoning, so cyclical reasoning, and we'll see how it's cyclical. And we need to be able to model number 1 and 2. And for that, we need this negation as failure concept. So what is negation as failure? So we have classical negation that you're very much familiar with. We'll represent it as minus P. So if I write minus sibling John, Jim, it states that John and Jim are not siblings. We know for a fact, I have a proof. I know John's father and mother, and I know Jim's father and mother. I know they're different. Therefore, they are not. I actually have an explicit proof. So explicit proof of falsehood of the predicate P is given to me. Only then I can conclude minus P. So you're probably familiar with the O.J. Simpson murder story where he killed his wife. Might have seen the Netflix movie, probably have heard about it. So, and I apologize for the gruesome example, but it drives the point home. So if I want to prove minus murdered O.J., Nicole, it holds true only if there's an explicit proof of his innocence. For example, I know for a fact that he was in Boston airport and the body was found in Los Angeles. Negation as failure, in contrast, is going to be represented as not P. And it really means that I made a good faith effort to prove P, I failed, therefore not P is true. So you see the difference, failure to prove versus explicitly knowing that something is false. So not sibling John, Jim, I make an attempt to show that John and Jim are siblings. I, for example, don't know the parents of John and Jim, and I might assume that not sibling John, Jim is true. So there is no evidence that they are siblings, and you assume that they are not. So we try to prove a proposition. If we fail, and so we do this all the time. We try to prove something, we fail, we conclude not P. So no evidence of P, then conclude not P. So here we'll say not murdered O.J., Nicole. We try to prove that he murdered her, and we fail, which is what happened in the criminal trial. And then we assume that he did not murder. So failure to prove versus explicitly proving falsehood, which is classical negation versus negation as failure. So negation as failure plays a very important role in modeling incomplete knowledge. So if we look at why classical reasoning has failed to model common sense reasoning, the reason simply is that we basically get stuck if things don't work out in classical logic. So if suppose we have axioms A1 through AN and we have a decision procedure based on classical logic that gives us a method for, say, proving theorems, and we want to prove the theorem T, and then this is how we'll write it, right? A1 through AN. T is a logical consequence of A1 through AN, axioms A1 through AN. We try to prove T and our proof fails. We are stuck. We really, in logic, you cannot do anything. You just fail. In many circumstances, as humans, we will say, well, if the proof failed, then it must be false. So most common sense reasoning is actually of this form. If we fail to prove T now, then T must be false, but it may become true later, but we'll worry about it then. And it's dual. If we prove T now, then T is true for now, but it may become false later because I discover some contradictory information. So for example, if I model reachability in logic, so I say X can reach Y if there's an edge from X to Y. And the transitivity clause, X can reach Y if there's an edge from X to Z, and Z can reach Y. I ask the query, given this graph, can A reach F? And you can see that the answer is no, but prolog proof will get stuck, basically. You won't be able to prove it. So if you want to define unreachability, you need explicit axioms for minus reach. When is one node unreachable from the other? So you see the problem? Defining reachability does not define unreachability. So it's really failure is, it's not that the logic is failing, it's just that how we interpret the rules. We could always interpret these rules as these rules here as if and only if. Instead of if, colon dash usually stands for if in Prolog. Say x reaches y if there's an edge from x to y. Turn that into an if and only if. Now we can say that if the right-hand side doesn't hold, conclude that the left-hand side doesn't hold. So reach x, y is false. And we actually do that all the time. So now what we could do, for example, is that, so we have map of cities, and some city you can, from one city to another, perhaps you can drive, but from other, other cities, there's no connectivity, no road, so you cannot drive. Then you could write a rule for, how to go from rules for how you can go from one city to another. But then if you fail, you could say, well, I'm going to take a helicopter. So you could actually write a rule like this: take helicopter to go from x to y if not reachable x, y. So you see, you can actually, so that's the critical part. I can write rules that draw a conclusion based on failure of a proof. We do this all the time, and that's the most critical thing, that being able to draw a conclusion from failure of being able to prove something. And so when we write, so most of the time we actually complete the rules ourselves. So for example, if I know that, if I have this knowledge that if I drop an object, it will break, then I automatically complete it. I will make it an if and only if. I'll say, basically conclude the dual as well, that if I don't drop the object, it will not break, which is true. But of course, it's incomplete because the object may break in other ways. It may be too brittle so that when you're handling it, right, it may break. So we do this all the time. We tend to complete the rules or make them if and only if. So again, I think I already talked about this, that this actually, kind of engenders circular reasoning, but circular reasoning was banned because Russell said so. After what happened, 100 years ago, I think 1915, 1916 timeframe, or maybe I think even earlier, 1800, more than 100 years ago. So the whole mathematics and logic enterprise is obsessed with having only inductive structures, inductive reasoning. And that's the crux of the problem, that for 50 years or whatever that AI has been around, we've been obsessed with inductive. We need circular reasoning or co-inductive reasoning as well, which essentially models circular reasoning. So for example, I might have rules say that Jack and Jill are very much in love with each other. And we have Jack says, I will eat dinner only if Jill, you eat dinner. And Jill says same thing, I will eat dinner only if Jack, you eat dinner. So question is, will they eat or not eat? What do you think? So I have two rules, Jack eats if Jill eats. Now, if you put this as a query in Prolog, question mark, Jack eats food, it'll go into an infinite loop, right? Keep calling. So the inductive world will say there is no model, it's false. Both Jack eats food and Jill eats food is false. But you can see there are two models, one world in which both eat and one world in which none eat, right? So both eat, or inductive semantics will say none eat because it's circular, say, oh, I cannot basically say unknown or false. This is not possible. But in reality, there's another model. So now non-inductive semantics also has to deal with incomplete information. So I might have rules which say, for example, John will teach databases if no evidence Mary will teach databases, and vice versa. Mary will teach databases if no evidence John will teach databases. What is the meaning of these sentences? So as a human, you might imagine two possibilities. In one world, John will teach and Mary will not. In another world, Mary will teach and John will not. So if you look at the rules, they engender circular reasoning, right? If you try to operationally execute Jack eats food, then you will get into an infinite loop. So you can actually find these multiple possible worlds if you stay in the realm of propositional logic, because I could say, right, Jack eats food if and only if John eats food, or sorry, Jill eats food. So, right, so P if and only if Q has two models, right? Both P and Q are true or both P and Q are false. So that's not a problem. But the problem comes when you go to predicate worlds. So propositional logic, we allow for multiple worlds, right? You're given a formula in propositional logic, and you're willing to accept, 200,000 models for that formula. But when it comes to predicate logic, we say, no, 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 you can only have one model, only inductive semantics. And I think that's the wrong thing that we have been doing for more than 100 years. So that's what we need to get over. And for that, you need co-induction and co-inductive semantics and multiple worlds. So even at the predicate level. So for example, I could write, I could actually write with predicates. So X will teach databases if no evidence Y will, where X and Y are distinct people. And it's dual. But in this case, since it's a variable, the two rules are more or the same. I should be able to find multiple worlds from this one rule. So you see that we think both co-inductively and inductively, and logic only allows you to model the inductive part. So that's the problem. And I would say that's one reason why logic has failed to model common sense reasoning. So answer set programming consists of rules of the form that you can see here. P is the head of the rule if A1 through AM holds, and no evidence that B1 through Bn hold. And then you could assert a fact that P is unconditionally true. It's a popular formalism for non-monotonic reasoning, has been around for a long time. You can also read this rule as you're trying to construct an answer set or a model, where you say P is in the answer set if A1 through AM are in the answer set, A1 through AM are in the answer set, and B1 through Bn are not. If P is a fact, it must be in the answer set. So your goal is to construct this model or the answer set, which is subject to these constraints. So that's another way, that's why it's called answer set programming. And you could actually have more general form where you have P if A1 through AM, not B1 through Bn. And then you could also have these classically negated predicates, where you say minus C1, which means you must have a rule corresponding to minus C1 to prove it. And then you could actually negate using negation as failure, classically negated predicates or propositions. And this actually also has a meaning. So these are called normal logic programs, and there are applications to node representation reasoning, planning, constraint optimization. I mean, there's 30, 40 years of research. And the semantics is given in a complicated way, but we're not going to describe that. And there are many implementations, S models, DLV, CLASP. In fact, CLASP wins actually, I believe, all the SAT solver competition. It's a really super efficient system. So more than 30 years of research. So the semantics is based on possible world, or what's called stable model semantics. You're given a program, there might be many worlds, many models of this program, and you will actually allow for all these worlds, these models. I'll give you examples. So the problem is that you're given an answer set program. How do you find its model? And model is assignment of true, false values to propositions, or later we'll have predicates, to make all the formulas true, and these models are called answer sets. And actually you can show it captures default reasoning, exceptions, preferences, constraint optimization, abductive reasoning, all kinds of things in a natural way. So again, red part is caveat, a little bit technical. So it's a better way to build automated reasoning systems and expert system. You can actually, model at least, the human thought process with this. Okay, we'll skip the caveats. So let's consider the college admission process. Okay, so we want to model the college admission process, and that will sort of, give you a good example. So college admission process, this is the United States, so it's a little bit different from here. No exam. So students apply, and if they have a high GPA, you admit them. But even though they have a high GPA, there might be some abnormal situations, like they might have a criminal record. So then you want to say, well, if they have high GPA, by default we'll admit them unless they're ineligible due to some reason, like they have a criminal record, or likewise they might have a special skill. So US universities will admit someone who's an athlete or good opera singer, or good at fencing or whatever. So if they have a special talent and they have a fair GPA, then also you admit them, unless again there is some abnormal situations or exceptions, criminal record, for example. Then you also know who not to admit. So now certain people are ineligible if they are not special. I know for a fact they are not special, and I know for a fact they do not have a high GPA, so the minus high GPA. And again, there might be some abnormal situations here that even though they're not special and probably do not have a high GPA, maybe the president of the university recommended this student, and you still have to admit that student. So minus eligible will fail in that case. Now, you could actually fail to prove both eligibility and ineligibility. In that case, what will you do? You will interview them. So you see the interesting rule? You fail to prove that X is eligible, you fail to prove that X is ineligible, then you interview them. So you see that you have this spectrum of possibilities. So if John has a fair GPA, does not have a high GPA, you can show that John must be interviewed. So essentially, with the classical negation and negation as failure, you can actually model hierarchy of truths, which are shown here. So P, if you write P, it means P is definitely true. If you write not minus P, what you're saying is, I have no evidence that P is false, which P means that P is possible or P may be true. Okay, go to the bottom. If I write minus P, it means P is definitely false. I must have a proof, remember. And if I write not P, it means I have no evidence of P, so P may be false. But if I am unable to prove minus P or P, then P is unknown. So you see that I can, so I have this 5-level hierarchy of modeling sort of the degree of truth. And this is what actually we do. So we could say food is good, food is bad, but we may also say food is not bad, not good, or unknown quality, right? And in fact, we humans do not use probability in our day-to-day life. We use defaults and exceptions. So we jump to a default, and then if there are exceptional situations, then we will take those into account. We do not say Tweety flies with a 90% probability, right? We just say, well, Tweety flies, and then we wait for exceptions. So if you look at the ASP systems that are in existence now, very sophisticated, but they all work by first, so you're given a program with variables, you will bind the variables to all the constants in the program in all possible ways, which is called grounding, ground the program, turn it into a propositional program, then you feed it to a SAT solver and some transformations to find the answer sets. So you can see that there are limitations to these ASP systems because they have to first ground the program, turn it, and then turn them sort of into data log, and then use a SAT solver. But there are many problems. Again, I'm not gonna. So you can only write programs that have a finite grounding, right? If the grounding is infinite, which you will have if you have, for example, lists or terms, you also get exponential blow up. So for example, I have this simple clause, P of X comma A if Q of Y, B, C, where X and Y are variables, A, B, C are constants. Then if I ground it, it will turn into 9 clauses. Now imagine a knowledge base with 50,000 clauses and 10,000 constants and 20,000 variables. This is an unsustainable process. So what you need is a query-driven implementation. Just like Prolog, you can pose a query, and that's what we did. We designed, but it's a non-trivial process because you need things like constructive negation and all sorts of advances. So I'm going to skip, not give you other problems. So the solution is to build these goal-directed execution systems, where you're given a predicate answer set program and you pose a query and you're able to get an answer, which is how we work. We have a goal, we have the rules, and we're able to reason sort of backwards. So only part of the knowledge base that is only relevant to the queries explode. In the grounding-based systems, you compute the entire model, which is completely useless. That's not what we do, right? We don't compute the entire model, all possible conclusions you could draw given a set of rules. We only work our way backwards and sort of prove the query that we have in our mind. So that's what you need. So we actually, so co-inductive logic programming is what allowed us to essentially build these predicate answer set programming systems. So we have actually the CASP system that we've designed, and many people actually use it now for things like treatment automation. And in fact, it's available as part of SWI Prolog. They've incorporated it. If you go there and you use their Swish interface, then there is a tab for writing CASP programs as well. But you can actually write these ASP programs with negation as failure and classical negation and execute them. It will also give you justification for the query, and you can perform abductive reasoning and all sorts of neat things. So the key concept for realizing this execution, goal-directed execution of ASP is the concept of coinduction, which is the dual of induction. And again, you may not be familiar with all this programming languages terminology, greatest fixed points and least fixed points. So when you do inductive reasoning, you're basically operating with the least fixed point semantics. For coinduction, you need the greatest fixed point semantics. So the idea here is that you detect cycles, and if you see a cycle, you know that if you assume, so for example, in the process of proving P, if P appears again, then P succeeds. And what we're really saying is if I assume P, then P holds. So for example, if I have these two rules that you have seen before, eats food Jack if eats food Jill, and eat food Jill if eats food Jack, and right, there are two possibilities, both Jack and Jill eat, and neither one eats. So both eat is in the greatest fixed point, none eat is in the least fixed point. So if I query, will Jack eat food? We reduce it to eats food Jill, and that reduces by the second rule to eats food Jack. Now we see that a goal that basically you see something appeared that's also present in the ancestor as one of the ancestor nodes. At this point, you say, oh, I'm in a cycle. This is part of the greatest fixed point. You stop, and then you say everything that is in the path that in my proof tree actually holds. So you find this coinductive hypothesis set, which is the model that both Jack and Jill will eat. What about the other model? I can ask its negation. Will Jack not eat? Reduce it to not eats food Jill, reduce it to not eats food Jack, and again you have a cycle, and you'll stop. And now you have a model in which both Jack doesn't eat and Jill doesn't eat. So you can see it's very simple, but then to introduce variables, it becomes complicated. So that's the idea, that I can execute inductively. So this part is inductive proof that none eat, and the previous one was the co-inductive one. So there's something called co-SLDNF. Again, I'm going to spare you the details. I already described them. But you can also have, okay, so human thought process can be largely modeled with default rules with exception and preferences. And I think I mentioned default rules a little bit to manage incomplete information, multiple possible worlds, which need cyclical reasoning, and global constraints. So examples already seen, right? I can write X flies if X is a bird, unless it's an abnormal bird, and penguins are abnormal birds. So if I have Tweety is a bird, Sam is a bird, and I ask, does Tweety fly? Does Sam fly? They will both succeed. Because I do not know anything about Tweety and Sam being a penguin, so Tweety and Sam must be able to fly. I conclude that not abnormal bird is false, not abnormal bird is true, bird Tweety is true, therefore flies Tweety is true. Now suppose we add the fact that Tweety is a penguin, and now you can no longer conclude that Tweety flies, because the not abnormal bird Tweety will fail. Abnormal bird Tweety succeeds because Tweety is a penguin. So not abnormal bird Tweety will fail, and therefore flies Tweety will fail. But Sam can still fly. So this is default reasoning with exception. So default reasoning is that normally birds fly. Tweety is a bird, it can fly. Unless exception, it's a penguin. And then you have cyclical reasoning, which is teach databases John, if not teach databases Mary, teach databases Mary, if not. And here you have two models. One world in which Mary teaches, John does not, other world John teaches and Mary does not. And then you can also have constraints which says Mary teaching databases is always false. So it will kill the world in which Mary teaches databases. So if I put these three rules together, I will get only one answer, which is that John teaches and Mary does not. Right? So constraints actually kill worlds. Okay. All right. So let's now see how we can model various types of reasoning that we do. So an example is aggressive and conservative default reasoning. So here, for example, you go to your doctor and doctor prescribes you a medicine, but this medicine may have side effects. So what are you going to do? What is your doctor going to do? The doctor may say, well, just go ahead and take this medicine. I think very few people have side effects. We're going to assume that you're not going to have a side effect, but who knows, that medicine might, right, kill someone. So you're performing, or you're doing default reasoning, but you're aggressive in making your decisions, your conclusions, jumping to conclusions, saying, even though this medicine may have side effects, I recommend you take it. But on the other side, I could be conservative. I could say, doctor could say, well, I am not, there might be side effects, so let's perform some tests. So what are we trying to do? We're trying to prove that this medicine will not cause any harm to you. Only after I have proved that it does not cause any harm, I will recommend that you take it. So now my reasoning is conservative. So aggressive reasoning, again, coming back to our bird example, you'll write X flies if X is a bird, not an abnormal bird. Penguins are abnormal birds. Tweety is a penguin. Tweety is a bird. Sam is a bird. And now if I ask, does Tweety fly? It'll say no. Does Sam fly? It aggressively reasons and says yes, without thinking about trying to prove that Sam may be a penguin. It says, let's jump to this aggressive conclusion. But then if I want to model conservative reasoning where I say, well, I don't know anything about Sam. Sam could possibly be a penguin. Let's try to prove that it's not a penguin first. Only if I fail to prove that Sam is not a penguin, I will say that Sam cannot fly. So you'll model it in this way. Like you can see here, X flies if X is a bird, not an abnormal bird. But now it's an abnormal bird only if I fail to prove that it's not a penguin. And now if Tweety is a penguin, Tweety is a bird, Sam is a bird, then for both Tweety and Sam, it will say no. Because now we're being conservative in saying that. So first we'll try to prove that Sam is not a penguin. Since I have no information about Sam being a penguin or not being a penguin, it fails. And we conclude that Sam, since I'm conservative, Sam cannot fly. You can also have strong exceptions where you might actually say, you have explicit reason to conclude that minus flies hold, that X never flies. Or if X is an ostrich, it never flies. You can also have nested exceptions. So I might say, animals normally don't fly, right? You see here, minus flies X if animal X and not an. But abnormal animals, which are birds, do fly. But there are abnormal birds, penguins, that do not fly. And possibly there could be, suppose we discover a subset of penguins called super penguins that can fly, then there's an exception to penguins as well. So you can model this. And in fact, most of our knowledge is default conclusion, exception to exception to. And in fact, you can actually channel this into what we're really doing is we are doing inductive generalization from observations. And you can actually channel this into building explainable AI systems, machine learning systems, which we have done. So we observe that many birds fly. So here are samples of individual birds. And these birds fly. So I write the rule. I sort of look at bird 1 flies, bird 2 flies, bird 3 flies, and so on. So I write the rule X flies if X is a bird. But then I discovered that there are birds that are penguins that do not fly. So I have my first decision boundary. So I have birds that do not fly on the right and birds that fly. So then I extend, I say, well, birds fly, but there are exceptions, namely penguins. But then I suppose hypothetically there are super penguins that can fly. So, but I then observe, oh, there are exceptions to exceptions. And so what you're really doing is moving, right, samples or maybe adding samples and sort of trying to revise the decision boundary as you go along. So you say, well, there is a super penguin green dot that can fly. So I have to move it from the right-hand side to the left-hand side. So I sort of change my decision boundary, right? Very much like a machine learning system, neural network, whatever. And now you will write X flies if X is a bird, unless it's an abnormal bird. Penguins are abnormal birds, but there might be abnormal penguins that are super penguins. So as I said, this can be basis for machine learning, and which we actually have done. So we have this family of algorithms, explainable algorithms called first order learner of default theory. So it's a little bit of a digression. So these algorithms actually will learn, given a tabular data, they will learn default rules. And they perform as well as I said, XGBoost, and so you can actually download them. So it learns rules very much like in inductive logic programming, right? So you can use information gain heuristics, or you can base it on Shapley values or Lime, but we actually have better heuristics that are based on gene impurity. And in fact, it produces an algorithm called fold SE, where SE stands for scalable explainability, which means no matter your data set size, it'll explain it in very small number of rules. So I'll just give you examples. If you take, for example, the famous adult data set. So what we're doing is, given data which is described in a tabular form, we're learning default rules. So we first try to cover the default conclusion, then we try to, things that were not covered, see if there's a pattern there, learn that as an exception. Then those things that did not get covered as an exception, see if we can learn exception to exception, exception to exception to exception, and keep going. And surprisingly, it actually works very well. So not only it competes with XGBoost and MLPs, it's also explainable. So we can actually explain the adult data set in just 2 rules with an accuracy of 0.84, which is comparable to, and then rain in Australia, these are all from UCI or Kaggle. Also in 2 rules, you can see 145,000 rows, 32,000 rows, 24 features, 15 features. And so here is the comparison table, where it compares Fold SE, which is, so the predecessors of Fold SE are available freely online, on GitHub on my homepage. Feel free to try it. But they will produce more rules. Fold SE, we got greedy, we're going to file a patent on that. It only produces very small number of rules because of the heuristics it uses. So you can see that sometimes XGBoost will win. The accuracy, it's in pink, whoever wins. Sometimes MLPs will win and sometimes B will win, but they're all pretty close. But the interesting thing is that, so the other interesting thing about this algorithm is that it does not need one hot encoding or any data preparation. Label the features, and just push it to the algorithm and it will actually learn the rules. So the execution time is, yeah. Hypothesis spaces. Yes, yeah, it's the same. But so decision trees, it performs better than decision trees as well. And interesting thing is that we thought this gene impurity heuristic will help decision trees perform better as well, but it does not. The size of the tree is huge. Whereas here you can actually explain things in 2 rules and 6 predicates. Whereas decision tree might take, 100 branch tree and, 600 predicates, things like that. So, but the interesting thing is the time. You see that it's very efficient. So we'll look at the average, 77 seconds on average for XGBoost, 42 for MLPs, and 1.3 seconds for Fold SE. So you can see it's orders of magnitude faster. Because, so again, why is it this way? Because of using this idea of default rules. That default rules actually represent knowledge very well. And you could say that that's what nature discovered. And that's why we think in terms of default rules and not in terms of conjunctive normal form formulas of the decision tree, right? Because we always think, let's work with what we have as we encounter, and then we say, well, we'll cross that bridge when we get there. We'll change our rule, add an exception as we get there. So you can, I'm sure you've seen this picture, right? If you're in machine learning. So you can see that fold will sit there. So decision trees sit somewhere here. Deep learn. This is explainability versus accuracy, but fold family. But again, this is a sort of a digression where I'm trying to show that if you try to emulate the human thought process, okay, so I'm coming towards the end of my talk now. So I'll just give you example because this talk is about automating common sense reasoning. So we have this, pieces of information, and I want to draw some common sense conclusions. So can I automate that? So we said George is a bachelor. George was born in Boston and collects stamps. Son of someone is a child who is male. George is the only son of Mary and Fred. A man is an adult male person. A bachelor is a man who has never been married. A traditional marriage is a contract between a man and a woman enacted by a wedding and dissolved by divorce. While the contract is in effect, the man is called the husband, the woman called the wife are said to be married. And wedding is a ceremony where you have bride, groom, bouquet. And I want to conclude that George has never been the groom at a wedding. Now, if you read these statements, can you prove it? Well, you see that George is a bachelor, and a bachelor is a man who has never been married. And what is a marriage? Is a contract between, marriage is a contract, husband and woman to be married, and somehow wedding has to be there. Yeah, number 7, traditional marriage is a contract enacted by a wedding, and a wedding has a bride and a groom. So you see that it's kind of long-winded if you want to prove that George has never been groom at a wedding, right? So can we automatically infer this? Truly commonsensical, yes. Yeah. Mary has an unmarried son born in Boston. So how would we prove that? We say, well, George is a bachelor. George was born in Boston. George is the only son of Mary and Fred. And George is a bachelor who is unmarried. So you can say the answer is yes. And then, then I asked, so this is actually from Hector Levesque's logic programming book, where he poses this. But remember that there are no answers to these questions. I mean, how do you automatically answer these questions? No woman is the wife of any of Fred's children. So Fred has a single child, George, and George is unmarried, therefore doesn't have a wife, and no woman is the wife of. So the answer to all these, so how would we model this? So we can actually model it straightforward manner in answer set programming and run it on our CASP system. George is a bachelor, birth city, George, like predicates, hobby, George, stamp collecting, son, X is son of wife, X is child of Y, X is male. And then the important part is the constraints that show that George is the only son. So what is the concept of an only son? If X is son of Fred, there's another son that Fred has, then another son not equal X must be false. So this is a constraint that declares what is false. And likewise for Mary. So with this, you're saying that George is the only son. And the rest of it is actually quite straightforward. But notice the introduction of time that you need, because marriage and wedding and divorce are time-sensitive events. Somebody could be married, divorced, married, divorced, married, divorced ad infinitum, right? How we model that. So X is a bachelor, if X is a man, and X never married somebody called Y at any time T. So you see the challenge now, negation standing in front of an existentially quantified variable. So you have to show that for every Y, for every time T, X, George, did not marry them. So you see the challenge of the proof, right? That you have to, but you can do all this in CASP, I mean, our system. So that's the power that it brings is just enormous. So here is X married Y at time T. If X is a groom, Y is a bride. They wedded at time T1, and time T is greater than T1, and they were not divorced at the instant T. And then you have to define divorced. X is husband, Y is wife, dissolved. And then you have to write a constraint that wedding always precedes a divorce. So you see that it's non-trivial to represent it, and you have a notion of time as well. So the CASP system also performs reasoning over real time through something called constraint logic programming over reals, which is embedded. And so you can actually model very sophisticated things. And so now I can simply ask, not groom George, and it will say yes. And then I can model unmarried son born in Boston of individual M, son is X, city is C. It's a general predicate. X is son of M, birth city of X is C, and X did not marry to any Y at any time T. And then so you can run these queries and they'll all succeed. And then likewise, Fred child wife Y stands for X is child of Fred, X married Y at some Y at time T, and Y is female, and it will succeed. Well, it will fail in this case. Okay, so I would have given you a live demo, but we don't have time. And okay, one more example. So I'll probably take another 4 or 5 minutes and be done. So this is the example of possible words. So this actually comes, so this problem comes from Hector Levesque's book. This one actually comes from a question posed by Peter Norvig on Quora. So he said, well, why does logic-based method do not work? And you can actually go and Google it. And he gave this example because let's look at this problem, he said. People can talk, non-human animals can talk, human-like cartoon characters can talk, fish can swim. Fish is a non-human animal. Nemo is a human-like cartoon character. Nemo is a fish. Can Nemo talk? And you can see that the answer is ambiguous. So Nemo is a fish. Fish is a non-human animal. Non-human animals can talk. So Nemo cannot talk. Nemo is a fish. Sorry, Nemo is a human-like cartoon character. Human-like cartoon characters can talk. So how do we resolve this? Now you already know the answer because I mentioned. So how do you resolve this conundrum? How do we as humans resolve this conundrum? Very simple, right? We separate the two worlds. We do not muddle them. We have no confusion between the cartoon world and the real world, which clearly, right, this thing tries to exploit by putting out that confusion. So I can model this. People can talk in all worlds. Non-human animals can talk in real world. Human-like cartoon characters can talk in cartoon world. Fish can swim in all worlds. So again, this is what we're trying to model. I mean, we could also have fish can swim in the real world, but not in the cartoon world, for instance. Fish is a non-human animal in real world. Nemo is a human-like cartoon character in cartoon world. Nemo is a fish in all worlds. And now I can start writing rules. Talk X if people X, minus talk X if non-human animal X, and RW stands for we're in the real world. X can talk in the cartoon world. So I'm using these two, RW and CW, to indicate which world we are in. If it works in all worlds, we don't put any qualifier. Fish swim in all worlds. I mean, swim X if fish X in all worlds. Non-human animals. Fish are a non-human animal in the real world. Human-like cartoon character Nemo in the cartoon world. And fish Nemo. We can actually take this. Well, now we need this circular rule, which says, if you're in the cartoon, if you're not in the real world, we're in the cartoon world. And if you're not in the cartoon world, we're in the real world. So we're either in the, so remember I described to you, Mary teaches if John does not teach. And so exactly the same. So you have two worlds, cartoon world, that's not the real world, and real world if you're not in the cartoon world. So if you ask, can Nemo talk? It'll actually give you a single answer. I mean, I could have given you a demo, but unfortunately, again, no time. So it'll tell you that Nemo can talk in the real world. And if you ask swim Nemo, it'll give you two models. Say Nemo can swim in the real world, but it'll clearly show you that either in the real world or in the cartoon world, and show you everything that's true in the real world for Nemo to be able to talk. And so then, so there are many challenges to building a predicate ASP system, and I'm going to skip that. You can read it all on the papers. You have to have dual rules to handle negation. You need constructive negation. So for example, if I say, I have a fact P of A, that P holds for constant A, and I say not P of X, then I should be able to get an answer saying, as long as X is not equal to A, P of X is not P of X is true, right? So I need to be able to say that X cannot have certain values. And then I need to be able to unify such variables. So it becomes complicated. And then you saw how we had, right? We had to universally quantify for married X, Y, T on the Y and the T. So we need universal quantification. So all these problems have been solved. I mean, we have this system called CASP, freely available on my homepage. There's a lot of information. And I said it's available on SWI Prolog. And we have used it to build many interesting systems. So this is a better way of sort of building an expert system. So expert system research is out of fashion because things didn't work out, but now reasoning has advanced. We know how to model. So you can actually build very nice systems. So we can, for example, this physician advisory system, there's actually a Finnish company. So we build a system for treating congestive heart failure. And we found it to be able to outperform cardiologists. So Finnish company actually using this system, and that's why they're working with SWI. So they incorporated our system in SWI Prolog. They're building a system for treating diabetes. Chronic diseases basically are ones where the rules are given, and so you can model them. Then you can do natural language question answering. We have built synthesizing concurrent programs, given the knowledge about concurrency and sequential algorithm and shared memory and automated legal reasoning. There are people using it for automating legal reasoning, autonomous driving. And this also gives you sort of a logic-based framework for reinforcement learning. right? Because I have rules that I learn, and then I encounter a counter example. How can I go and modify my rules so that this counter example can be taken into account? So all sorts of interesting things become possible. So, okay, I'm gonna skip because, so the two key papers, so you can again find them. This is unpublished paper on arXiv here, the original paper. And this one is from the Logic Programming Conferences. It describes the CASP system, but there are tons of papers describing all this. So the road to AGI, current focus has been on machine learning and deep learning. The goal has been to use machine learning for realizing advanced general intelligence, even chat GPT, everybody was talking about, even advanced super intelligence. So our thesis is that it's not possible without reasoning capability, because if AGI was possible purely based on machine learning, then nature would have produced it already. So nature has produced, so machine learning corresponds to our senses. So we're able to see things, right, and sort of pattern match. This is the light, this is the projector, and so on. And that's another interesting thing, that things that are based on just recognizing on our senses, we have a hard time explaining also, right? Explainable AI is a huge problem. If you ask me, why is this a projector? Or why is this a cat? I'll have a hard time explaining, because whatever description I come up with may apply for other things as well. So for those things, for such things, explainable AI inherently is a hard problem, because as humans, even we cannot explain, right? Why is this a chair? Or maybe I will come up with some description, but then it might apply to other objects as well. So nature has produced animals like dogs that have better sense, eagles that have better eyesight. So nature tried very hard to use machine learning type thing alone to produce an intelligent being, super intelligent being, but it failed. It had to resort to reasoning to produce us humans. And as you go up the evolutionary chain, you see that reasoning abilities improve, right, culminating in humans. So my argument is that you cannot build AGI unless you incorporate reasoning and common sense reasoning. So we saw, again, default reasoning, that it works so well, even with machine learning, generalizing. So the idea is to use machine learning as eyes and ears and, smell or whatever, nose, and translate this input into knowledge predicates that sit in my head. And then we capture common sense knowledge. So we model whatever we have learned over 20, 30, 40, 50 years, represent that in ASP. So it will be an arduous task, but once we have it, it's there. It doesn't change, or you might keep adding to it, and then perform reasoning over this knowledge aided by your common sense knowledge. And you actually build systems, so autonomous vehicles. So we're working on that, where use the cameras and the sensors just for building a model of the world, and then use common sense reasoning to actually make a driving decision, which is what we do as humans. We see a red light, we explicitly reason that I must brake, right? Or I see a human pedestrian, and that's why we're so good. And in fact, if you look at a machine is very good at very quick. It has no trouble in right. You can design steering control and brake control and all that stuff is super easy. It's being able to tell that recognize the red light and stop and blah blah. That's the hard part. For humans, is the other way around. When we were learning driving, the hardest part was, how to brake and how to change gears and steer, and that's what you have to learn. But knowing that I should stop at a red light is very. You give a 5-year-old a toy car, they can drive around this room with no problem without bumping into anything. So and why is that? Because we're using our common sense reasoning. We're using reasoning for driving, not machine learning. And then we're also building chatbots that really understand what a user is saying. So very narrow. So for example, a concierge who can answer questions about choosing a restaurant, or you come to the university and there's a front desk person, which is a chatbot, and you say, oh, I want to find, where's my professor's office? And the system says, well, what's your professor's name? And it says, I don't know, which actually happens. Okay, so do you know the room number? Okay, which class is it? Student could say, I don't know. Do you know the TA's name? Yes, I do know the TA's name, maybe. So from there, then you can go look up and sort of determine which class the student is in by looking at the records, and then direct the student, right? We should be able to do that, right? That's what a human will be able to do. And then automated question answering, the same idea, that translate English text into predicates or knowledge. and then use common sense reasoning to answer questions. So we actually tried this on the baby data set, which I'm sure many of you are familiar with, the paper in AAAI 2021, where you can basically get 100% accuracy. Because there is no reason why you cannot, because if you didn't get 100% accuracy, it means there was a gap in your knowledge. So you go back and fill that gap and you're done. So you can get 100. So I think on all the data sets that we tried. So baby data set is where you have short stories where you say, John was in the living room, he picked up, was in the kitchen, he picked up 4 apples, he went to the laundry room, he put 2 apples down, then he ate 1 apple, then he went to the living room. How many apples are in the living room? So we are able to answer these kind of, so we actually understand, build the knowledge base and answer those questions. Okay, so conclusions. So sorry, I'm a little bit, automating common sense reasoning is the holy grail of AI. For automated common sense reasoning, we need default rules, global constraints, and assumption-based reasoning. So progress has been stymied by singular focus on inductive structures or single model. So we work with ASP, which allows multiple worlds, multiple models, non-inductive reasoning. And we have this CASP system. And in fact, you can think of our system as giving an operational semantic. There's actually an operational semantic. In terms of related work, there are many works, but they lack in one or more key aspects. I'm sure many of you will talk about the psych system, right? CYC psych system, the 20 years of work. And the problem was that it has something like 1,200, more than 1,000 reasoning mechanisms. So the problem, how do you know which reasoning mechanism to apply? So here our goal is keep it as simple as possible. Only default rules, constraints, and multiple possible worlds. So keep it simple, and then I'll be able to. So maybe I will not cover 100%, but I can get 90%, 95%. So many, there is workshop we hold every year on these aspects. You can see a lot of interesting papers there. And sorry for being over time, 5 minutes, questions, and a lot of information on my homepage, including free systems and that you can download. Okay, questions? Too much information, sorry about that.
So I had a very trivial doubt. Can you go to the slide that you were showing the George case? Where
Okay.
Yeah.
Sure. So go to the, yes.
One slide, yeah. So over here, I just wanted to ask the first inference that or the conclusion that we got that George has never been the groom at a wedding. It might also be false because let's say George was married at a point T dash. So let's say the current time is T and George was married at some point T dash and then was divorced after that time T dash, but before time T. And according to the 9 rules that we have, marriage is dissolved, right? After a divorce. So George might again be a bachelor, right? So even though the first two, in this case, the first rule will also hold where George is a bachelor, but it's also possible that he was married at some point, therefore he was a groom at a wedding. So do you think that?
Right, so good question. So remember that we are saying we will only work with the knowledge we have. So if we don't know, we assume that it's not true. Right. So yeah, so basically since there's no information about George being married earlier or being divorced, we assume that that was not the case.
Right.
So given just this knowledge, and if you wanted to model that, sure, you could actually model it, but then you'll have to say George could possibly be, so you might say it's possible that George was married or not married. And so then you'll have 2 worlds, one world in which George is married and one world in which he was, married and divorced in the past, one world in which he was not married. And then in that world, you'll get a different answer. In this world, you'll get a different answer. So it's up to you, really, but you need that knowledge. So here we assume that since no knowledge, assume it's all false.
Right. So I completely understand that point. I mean, the reason why I thought of that was because in one of the rules, the divorce was mentioned, right? And I felt that maybe that information might be important, sure. Which in the context of this rule. So my question then is, if we are taking all the rules to be absolute and the inferences that we can get from them, what is there some level of assumption or some level of guesswork that you think we should also incorporate to make our models more accurate? So in this case, let's say the later two conclusions definitely hold true, but the first one might not hold true in one of the possibilities, whereas there are no possibilities for the other two conclusions. So should we also model such kind of assumptions, and doesn't that increase the complexity, but also ensure that we are not taking some edge cases into?
Sure.
Yeah.
I mean, if you certainly you can model that, but then you'll have to state that George could possibly be married and divorced.
Okay.
If you state that and we model that, then exactly what you will get. But if you don't say anything, we'll assume that. So since negation is failure, I try to prove that George was married in the past and divorced, and I fail. So therefore, I conclude that George was neither married nor divorced in the past.
Makes sense.
So that's basically
Yeah.
So you can absolutely model that, what you are saying, if you want to, but you'll have to add that information that George may possibly be married and divorced in the past.
Makes sense. Thank you. So I had another question.
Sure.
So you mentioned that this methodology or framework can also be adopted for reinforcement learning. So one of the major problems of RL right now is that there's a huge lack of interpretation as to how RL models work, because the variance is extremely high in sense as to how the agent is learning, depending on the various reward function that we're assigning. So how do you think that using this kind of a framework will help us in getting a better interpretability for RL models per se?
So I mean, again, I know very little about machine learning. I'll be honest, all my life I worked mostly on reasoning. So I mean, I'll try to answer, but I don't know if it'll be. So here, I mean, the idea is that, so think about how do we learn? I mean, we already have the knowledge, and as we are going along, we encounter things that do not work that work, and we keep revising those rules. So the same idea is here, that we keep revising our rules. So we're trying to write the classical. So there's a lot of these text-based games that people, in fact, and I have a student who actually applied this methodology for reinforcement learning in the context of text game. And I think there's a paper in some workshop last AAAI. So more details are there, but the idea is that you try to learn the default and the exception. So once you encounter something that will get you a negative reward, then you can add that as an exception, possibly, so that your inference will be correct next time. So that's the basic idea. And that's how we work as well, right? We see enough examples, we add of some exception, then we add that as an exception. If we see enough examples of a default. So basically, the whole idea is that you keep learning the default conclusion and the exceptions as you go along. And then you keep modifying your rules if needed. So that's what he was doing. I think he forget this text-based game. In fact, I think it's Microsoft that has published this very popular game that everybody uses for RL, for a text-based game. Okay, sure, possibly. So his idea was that, okay, first you learn using that fold algorithm, he will learn the rules. And then as more and more things show up, he will modify the rules as we go along by either adding an exception or extending the default. So I mean, that's how we operate as well. In fact, you could even use this framework for explanation-based learning, where you learn from just a single example, right? So I could generalize from one example, and then as I go along, I either modify it or I check the veracity of this rule and maybe discard it. So I mean, so there's lots of stuff to do, given that we can model common sense reasoning, with all these explanation-based learning reinforcement, but a lot of it is work in progress. So anybody wants to try it out, join the effort, by all means. These systems are available, and there are people actually using them for actual problems. So hopefully that answered your question.
Yeah, I had a question. In the system you described, in which you learn the default and then learn exceptions, how do you tune the extent to which the system overfits or does not overfit to?
Okay, so good question. So I think, again, I'm not really an expert, so a lot of this work is the work of my student. So
okay.
he eliminates the long tail, basically. So at some point you say, too many, you're going too far into exception to exception to exception. I mean, up to what level can you keep going? So you stop at a certain level. So you cut the long tail, basically.
Okay.
So
that would be okay. That would be like a hyperparameter that
yeah, there's a exactly. There's a hyperparameter you can choose as to how far you want to go down this, rabbit hole of exceptions.
Okay. Another question was like, how does this differ from like just pure inductive logic programming? Like, because you're learning
Yeah,
the
so
same
it's
sort
very
of
much like inductive, but inductive logic programming does not learn answer set programs, does not
Okay.
learn default rules.
Okay.
And the negation that they learn is not the greatest. I think there's some, so it's more complicated basically. So whereas here we're learning a default theory. So ILP will learn logic programs, but they'll be positive logic programs.
Yeah.
And negation even has a different meaning.
Okay. Okay. Yeah. Thank you.
Yeah, I think Lou has a question. Lou has joined online. Lou, please go ahead and ask. She has a
Okay.
hand.
Thanks. Thank you, Professor. I have one question.
Sure.
The question is, what are the relationship between causal structure discovery and logic rule learning? Because I think both
Causal
of
structure
these
discovery.
two.
I mean, yeah, it's very similar. Again, I don't know much about causal structure discovery, but I mean, this would be one way of discovering, causal structure. Again, I'm not familiar with that. Again, as I said, not really an expert on machine learning, so anything I say, take it with a grain of salt. But this could be one way of, right, also describing. Now, see, causality is hard to establish because for causality, you need to be able to establish sort of the if and only if relation, right? So B causes A if you can conclude A if B, but you should also be able to conclude not B. If B is not there, then A is not there. So this is sort of a one-way street here. So causality, and I don't know how the other work established causality, but in general, learning right causal behavior is really hard because you need to learn the if and only if. So, but this could be one way of learning causality. We actually did explore that, but the challenge is, the if and only if part, that you have to show that if B implies A, then you have to also show that not B implies not A.
Okay,
Hopefully that answers your question. Yeah.
Thanks. And I'm wondering if I can ask a following question.
Sure, please.
What is the difference between the logic rule learning and the decision tree? Because I think both of them can a set of if then rules.
Excellent question. Yeah. So decision trees are so the way we represent knowledge, which is default rules. Knowledge representation is actually much more succinct. So as I was saying earlier, if you learn, for example, the decision tree for, unfortunately, I don't have. I mean, I have. It's in fact, you can find papers in my homepage comparing decision trees and this method. So decision trees will be much bigger in size and will have much more features or predicates. Whereas here, we're able to explain it in 2 rules and 6 predicates, and decision tree might take 50 rules and 30 predicates. So decision trees really are more like, I would say, conjunctive normal form formulas, sort of. So this is a more succinct representation of knowledge, and I think that's why. So, and also, as I was saying, we use Gini impurity to get this scalable explainability. Interestingly, that does not improve the economy of rules for decision trees. And again, all this is in a paper that's on my homepage.
Okay. Thanks. Thank you so much.
Sure. You're welcome. Sure. Go ahead. Yeah, please.
So so this question is in context of the work that I do here. So basically our work was to understand toxic queries for text prediction that come in Edge and Bing. And we basically wanted to create toxic classifiers accordingly. The problem right now is that for products like Edge and Bing, where text prediction happens, if a certain word which might be racially offensive or in some other term, if that comes up, then we just block the query. But there are some certain words which, when put in the correct context, right, might not be harmful. So for example, let's say black. So black is currently a word which is in the block list, but black might also occur in context like I need a black car or something like that, right? So in that context, it's not harmful.
Sure.
So my question is that if I have to create an analogy with the framework that you've talked about, do you think using such kind of a framework for NLP, such NLP problem statements might be relevant or useful, given that understanding that context change is the most difficult part. And how do we use the,
good question. Good question. So there again, what we really need is, as humans, we're able to tell, of course, right? So what we really need is, given a text, a sentence, can we translate that into predicates? And then we apply our common sense knowledge rules to say, is this, racial state, race-related statement, or, bias statement, or proper statement? I mean, you have to do that. Other than, if you really want to, we could do pattern matching, machine learning, whatever, but eventually we have to understand what the sentence is saying. And that's the argument. So the way to do that would be, take the sentence, convert it into predicates, and then essentially you have all these common sense knowledge rules that we have modeled, which is again the hard part. So we'll know that, a black car is okay, but, black and anything human related is not okay, something like that. But it's challenging. Again, we're not there yet. So that's why I hope that the community one day, or sooner rather than later, and we're actually trying to do that for very narrow domain, be able to translate text into predicates. Just as we translate English into French, can I translate English into predicates? And this is exactly what we do, because when we hear a sentence, even though it is ungrammatical, we're able to translate that into knowledge and that as predicates, and it sits in our head, right? And then we reason with that. Can we have a system that does that? So for this chatbot project that I mentioned, we're trying to build one for, hotel concierge, where I can go and ask, can you recommend a restaurant nearby? And then it'll do, ask you for your preference, blah, 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 and then price range, etc. But it should, no matter what you say, it should be able to, just like a human, it should not falter. For that, you have to understand, right? So given a sentence, we extract the knowledge as predicates. So that's what we're trying to do. But we do not find any data sets or any effort. So maybe, Microsoft can do that. We got the resources. But you see, right, simply translate English text into predicates, some type of. And the other interesting thing is that you have to necessarily translate knowledge as default rules. So there are all this work on knowledge graphs, for example. Now, if I use knowledge graphs and I ask Tweety is a penguin, Tweety is a bird and Tweety is a penguin, does it fly? I don't know. It'll probably say, yes, it flies. Because it does not associate so that's another problem I see, that knowledge graphs are all designed with, simple-minded way, if then else rules. But that's not how the world is. We need to move to default rules so that we also have the exceptions. So yeah, so it's hopefully in the near future somebody will actually build that. We're trying to build a small version of it. But unless you do that, you cannot. You can use pattern matching, and your pattern matcher can build better and better and better. But humans are creative. They'll always try to slip things in. It's like you read the comment section of newspaper articles, and people will introduce cuss words in very creative ways because they know that the filter will remove it.
Even sarcasm detection would be a problem in that sense. But yeah, thanks a lot. Thank you so much.
Sure.
Very helpful.
Okay, thank you so much. Yes, thank you for going beyond the hour. That's the problem with professors. They want to tell too much. Okay, all right. Thank you.